We're going to think in this particular class and video about the idea of taking samples from populations and the concept of a sampling distribution. So what's this about? So the way to think about things is pretty much any time we do any statistical analysis, we're actually not working with all of the data that's available to us. We're only working with a subset of the data. And therefore, the conclusions that we draw are only estimates of the truth. And what we really want to do is communicate our uncertainty about those estimates in the way in which we present the results that we find. So if I'm interested, for example, in knowing how many times people use particular medical services, I don't necessarily have all the data of everybody in the population and how many times they go to the doctor or whatever health services we're interested in. I've just got a sample of people, and based on that sample I want to make some kind of estimate about what the population's overall usage of medical services is. So how do we think about that? What we're going to do in this particular video is kind of come up with some of the theoretical ways of thinking about it and the theoretical results. And then towards the end of it, we'll start to see how we use that theory to guide our communication of results in such a way that we communicate the uncertainty and the lack of precision in the results that we've actually got, the fact that they are estimates. Okay, so how do we think about it? Well, we think about things in terms of a population and a sample. So we have a population of all the people in the area of interest, which might be all citizens of Australia, or it might be all students enrolled in this course, or whatever it might be. So that's everybody, and that population has some characteristics. In particular, for simplicity, we're just going to think about one characteristic of that population. That's the mean. So what's the average number of times people go to the doctor out of the population of all Australians, for example. So that quantity that we're interested in is known as a parameter. It's the mean in this case, but it could just as easily be, the median, or it could be some other quantity. But for now, we're just choosing the mean as the most commonly used parameter. Okay, that's what we'd like to know about, but we actually don't have enough information. We haven't gone and talked to every one of the 26 million people in Australia to ask them how many times they go to the doctor. Instead, what we do is we take a random selection of people within Australia, and we call that a sample. And based on that sample, we calculate the mean of the sample, x bar, and we use that mean to estimate the population mean. And that process of estimating the population mean is what's called inference. It comes from the word infer. So from this sample statistic, we infer something about the population parameter. Notice some of the jargon we're using here. We've got a population with a parameter, which is a characteristic of interest. We have a sample with statistic, which we can actually calculate because we've got the data, and we use that sample statistic to estimate the population mean. That's the world we're in. Okay, so that's the framework we're going to work things in. So there's two things we're going to focus on here. The first one is just a sort of we've mentioned this very briefly before, but need to think about, first of all, everything that we do with this kind of framework, everything that we do with that sample statistic and using it to say something about the population mean, depends critically on the sample being a good sample that's representative of the population. If we've collected our data in some obscure way, where we've only got all of the Australians who live in New South Wales, for example, in our sample, instead of all Australians across the country, then we're not going to get, no matter what we do with our sample data, it's not going to give us a very good estimate of the population characteristics. So what the sample has to do is be chosen randomly and make sure that it represents the characteristics of the population. So things can go badly wrong in that whole process of getting a sample in a few ways. One is with the design of the questions that you might actually ask someone. It's simple enough if you ask, how many times you've been to the doctor in the last 6 months. Well, you probably won't do too badly with that. But if you are asking perhaps more opinion-based questions, you can imagine that the wording of the question would make a difference to the kinds of answers you get. So here's a couple of examples here. The first question is worded in a very bad way, in that we're asking people to make a statement about their opinion of a politicians, but we've really skewed the information in a certain way to favour one politician over the other. So you can muck up the survey. Now, the point is, it doesn't matter what fancy statistics you do with your data after you've got this information. You just can't trust anything you get when you've got questions like that. So you've got to make sure that you're asking sensible questions. Okay, that's just, and then second area where you've got to make sure you get it right with this sample is in how you choose those elements in the sample. How do you choose the subset of the population that you're actually going to collect your data from? And the key thing is that it needs to be representative of the population. So my sample quantities, my sample data, those 100 or 1,000 or whatever number of people that I've surveyed, need to be representative of the overall population that we're interested in, such as the population in Australia. Now, there's a couple of ways that can go wrong. The first one is with what we might call selection bias. So that is where we choose people in a particular subset of the populations. And I gave the example before of just choosing people who live in New South Wales. That's clearly going to not give us a representative sample. Or perhaps if I'm interested in guests at a hotel, that I only walk, I'm brave, I have to interview them one by one, but I'm not very brave, and so I only walk up to the people who look sort of nice and happy and friendly. Well, clearly they're going to more likely to give me positive feedback, so I get a bit of a distorted picture. That's a pretty silly example, but actually not surprisingly, it is actually a problem that occurs in common. So the solution to selection bias is simple. Take your sample randomly. For example, here, just choose particular guests of the hotel at a particular point in the time and ask them to answer your particular survey. And this is just a simple way of making that randomness. Okay, so choosing a random sample ensures that the sample is representative, unless when after you've chosen that sample, a whole bunch of the people refuse to answer your questions. So you can randomly choose a bunch of 1,000 people and ask them to fill out a survey, but if half those people say, no, I'm not interested, then you end up with potential bias, because there could be something about the people who choose to not bother answering your survey. Perhaps they're people who are particularly disappointed with your hotel, and therefore they're not even interested in giving you the feedback. So the responses that you do get are going to be more favourable than what the overall is. Or perhaps it's the opposite. Perhaps the people that bother to fill out your survey are the ones who've got a lot to complain about. So you get some good feedback, but at the same time you get an average result, which is worse than what the truth is, because the happy customers didn't bother to fill out the survey. So non-response bias is tricky. In this particular example I've given, I can't even tell which direction the bias is likely to be in, because I just don't know the motives of the people who choose not to respond. So I've got to think about that whenever I take a sample, and there's ways of dealing with that. Most importantly, what you probably normally try to do is provide some incentive for people to respond. So once you've selected them for your sample, you really want to get them to respond. So offer them some incentive, a little reward if they fill out the survey or whatever, for example. Okay, so that's around getting those dots in the sample, that group of people here, making sure that that's giving me the best sample that's representative of the population. Okay. Now we've got to think about what we do with that sample of data in calculating some kind of statistic which provides us with an estimate of the truth. So we're going to do the obvious thing, which is if I want to estimate the mean of a population, the obvious thing to do is to take the mean of the sample and use that as an estimate of the population mean. Now, of course, as soon as you do that, one of the things that strikes you straight away is that every time you take a sample, you may get a different answer. So because you're going to take a sample from a different subset of the population. And one of the things so immediately you have to remind yourself of that whenever you draw conclusions from your sample, that it's only an estimate, and you need to communicate some of the level of uncertainty about that estimate, so that you can say, look, I've got an average number of times people go to the doctor of 3 times per year, or 3.3 times per year. And we estimate that's the average number of doctor's visits for all Australians, but we're not 100% sure that's right. It could be 3.4 or 3.1, or could be as many as 4. It could be as low as 2.5 visits on average. So you'll qualify your estimate with some kind of statement along those lines that just reflects the uncertainty. Okay, so that's what we want to get to. That's the sort of additional information we want to provide users, and that's very important, because if you just come along with the magic number, 3.3, this is it. This is exactly how many times people go to the doctor, and you plan all your hospitals and doctors, surgeries and so on according to that number. And if that number, being only an estimate, if it's not actually right, your planning may go astray. So you want planners to factor in the uncertainty. Okay, so how do we get to those kinds of qualifying statements? Well, we're going to have to do a little bit of theory, and we're going to have to come up with a theory of something called the sampling distribution in order for us to know how to capture uncertainty in our use of a sample statistic as an estimate of the population parameter. So to explore the theory, let's do a baby example. Suppose the population just comprises of three companies, company A, B, and C, and you can buy shares in these three companies. The share price of those three companies is $3, $5, and $7. Easy. So, and you want to estimate the average share price. Now, you wouldn't bother taking a sample in this case because there's only three numbers in the population, but suppose we're going to imagine that we would take a sample. Now, in this case, because we have the whole population, we actually know the true answer. The true answer of the mean share price is $5, okay? So that's deliberately chosen example where we know the truth, so we can see how we go at estimating that truth. And what we're going to do is take a sample of just 2 shares and use those 2 shares to estimate the mean. And sometimes we'll get $5 for the average, sometimes we'll get less. So for example, if I choose shares B and C and get the average, it'll be $4. So my estimate, my X bar, will be inaccurate in estimating the true value. Not too far off, but off. So sometimes, by chance, I'll actually get exactly $5 for my sample mean, but most of the time it'll be something a bit bigger or something a bit smaller. So let's imagine we took every single combination. Here's all the samples we could get of 2 shares. Remember your permutations and combinations from high school maths, all the different combinations, all the different values, and then all the different X bars you get. So you can see that in only one of the cases, in 3 of the cases, I get an X bar of 5, the truth. So 3 times out of 9, my estimate is correct. The other 6 times out of 9, it's incorrect. Sometimes a little high, sometimes a little low. And that's precisely the uncertainty that we know exists anytime we use a sample quantity to estimate a population parameter. There's a couple of things that are interesting about that. We can actually write down all the different possible X bars we got there and their probabilities, and you may recall what you saw on the previous page was that there was 3 times out of 9 that we got a 5 for the mean, and we got a couple of 6s and only 1 7 and so on. So we can actually work out the probability of getting those different sorts of sample means. And you can see it's as low as 1/9 for X bar equal to 3 and as high as 3/9 for X bar equal to 5. And that allows us to make statements like these ones here. Okay, now this table here is what's referred to as the sampling distribution of X bar. It is the set of all possible X bar values and the probability of each of those X bar values occurring. Now I've constructed this using an entirely kind of silly artificial kind of thing. I mean, nobody ever calculates a standard sampling distribution this way. Why would you bother looking at all the possible samples? The point is, in practice, you only ever take one sample and you use it to estimate the characteristics of a population that you don't know anything about, except for what you learn from your sample. But this is a theoretical exercise. One of the things you notice is that if you calculate the mean of these X bars, you actually get 5. So when you use that's quite important. That means that when you use a sample quantity, like the mean, to estimate a population quantity, the population mean, on average, your value will be getting it right. So sometimes my X bar will be a little bit too high, overestimate the mean. That's what happens, for example, when I go to 6 or 7. Sometimes it'll be a little bit low. It'll underestimate the mean, like 3 or 4. Once or twice, it might even get it exactly right. But on average, if I was to keep trying samples and getting X bars, on average, I would get it right. So that's comforting. So there's no systematic bias in my use of the sample mean to estimate the population mean. It might be 100% accurate, but it's not going to be consistently overestimating or underestimating the mean. That's good news. There's a bit of mathematics that we can do here to show that that's exactly what should have happened. That was just what we found in this example, but given that the formula for the mean is just the sum of the values, sum of the xi's on n, and the mean is the expected value of that, the expected value of each of the individual xi's is mu, so I'm going to sum a bunch of mu's and divide by n, so I get n times mu on n, which is mu. So the X bars on average will equal the mean mu. So that says it's an unbiased estimate. We can also apply slightly more complicated mathematics to the variance, and this is what we do here. There's a result that when you calculate the variance of constant times something, then it's the constant squared times the variance of the something that gets produced, and that's what you've got here. So that's why there's a 1 on n squared, and that's because the variance itself involves squaring the data. So if you scale the data by 1 on n, then effectively the variance is scaled by 1 on n squared, because it's a squared quantity. I won't go through every step of this maths, but you can derive the formula down the bottom of the screen here. And this is the formula for how much variation there'll be in my x bar around the true value if I were to take many, many samples of x bars. That's a pretty useful quantity because it gives us a bit of a clue about when our x bar is going to be good, providing us with a good estimate of the mean, and when it's not such a good estimate. Here's what, for example, things look like if I'm trying to estimate the mu, and the mu in this case, the mean, equals this amount here, which actually is 0. So I've got some data which, for convenience, has a mean of 0. If I take a small sample, my estimate is not going to be very accurate. That makes sense, doesn't it? If you want to estimate the average number of times all Australians go to the doctor and you only take a sample of 10 people, you're going to get a pretty inaccurate estimate. It might be too high, it might be too low. But it's going to be okay on average, but any one estimate you've got could be a fair way from the truth. If I take a sample of 100, I reckon my estimate will be more accurate. If I take a sample of 1,000, it's even more accurate still. So this series of normal distribution curves captures that idea entirely. That is that the more I take in my sample from 1 to 4 to 25, the sampling distribution of x bar gets more and more narrow and tightly grouped around the true mu value. So I'm estimating the truth more accurately. And that's precisely because the variance of my normal distribution is sigma squared on n. So as n gets bigger, I'm dividing by a bigger number, so my variance is getting smaller. Okay, so that's what's going on there. Excuse me, I'll just ignore that call from my daughter. Carry on. Okay, so that's an important result. So it kind of confirms what intuition tells us, which is that the bigger your sample, the more accurately you're going to estimate things. There's a little bit more to that as well, but we'll leave that for now. I've jumped over something here, which I'm just going to go back to now, which was when I drew this sampling distribution of x bar, I centered it on the true value, mu. I say its spread is determined by this formula here, but I also drew it as a normal distribution. Why is that? Well, if the original data x is normal, then x bar is going to be normal too. It's kind of obvious because x bar is just the sum of the x's on n. So I've got a bunch of normally distributed variables, then I average them, then the average is also going to be normally distributed. So that's one reason why I drew the normal distribution. But actually there's a theorem around called the central limit theorem, which is kind of neat, and we're not going to spend long on this, but it's just worth mentioning in passing, that even if the original data is not normally distributed, averaging that data for a reasonable size sample will kind of get rid of the non-normal shape of the distribution and make it look more and more normal. And so the sample mean will actually follow a normal distribution or approximately normal distribution as the sample size gets bigger. And that's referred to as the central limit theorem. Enough on that for now, but just worth noting. So what we can do is we can now make use of the three things that we've kind of learnt about the sampling distribution of x bar to do some useful things with that. And remember, address our overall goal, which is to be able to make statements about how uncertain this particular estimate of the mean is, given the sample data that I've collected. So we've got, let me take you down here. So we can't say for sure how close x bar is to mu, because we don't know the truth in most cases, but we can say something about how accurately it's estimating it. And the key way in which we do that is with this sampling distribution of x bar, sigma x bar, which is sigma on the square root of n. So for example, suppose the students in this class have an average age of just under 20, 19.8 years. Standard deviation of the ages is 3, and I take a sample of 100 students. How accurately can I estimate the truth? Now, sorry, no, that's incorrect. This is not the population mean, this is the average of my sample. So I've sampled 100 of you, and I've got an average age of 19.8 and a standard deviation of 3. How accurately is this number here estimating the true average age of all students? Answer, take 3 divided by square root of 100, which is 10, so 3 on 10 is 0.3. So on average, my X bar will be estimating the population mean with an error of around about 0.3 years above or below the truth. So when you look at 19.8 and you say, I estimate that's the average age, and people say, but how accurate is that estimate? You can say, well, it's not going to be 100% right, but it's not going to be too far off. It's going to maybe be out by 0.3 of a year, maybe a bit more than 0.3 of a year, maybe a bit less than 0.3 of a year, but it's not going to be out by 1 or 2. It's going to be out by a lot less than that. Okay, so that gives you an idea about how accurate your estimate. Okay, so that's one of the ways we get indication of how close X bar is to mu, by calculating this quantity here and interpreting it as a judgment call as to whether that looks like an accurate estimate because of the size of that. Okay, now that's fine, but we actually can do something a little bit more formal than that. And so what we're going to do is make use of the sampling distribution to sort of come up with what we call confidence intervals. Step towards that, first of all, we can actually, so the confidence intervals comes next, but before that we're going to just think about a sort of another way of making use of the sampling distribution to kind of essentially rule out or eliminate the possibility of certain values occurring. So, and that's kind of not practically something that we do very often, although we do indirectly use these kind of results here when we do something called hypothesis testing, which will come a little bit later on. Hypothesis testing is the idea that certain kind of values of the mean might be particularly interesting to us, and we want to see whether we've got any evidence to support those values being valid, or any evidence to suggest those values are not true, to be more precise. And so we make use of the sampling distribution to help us with that. So here's the idea. I've got an X bar. I'm using it to estimate the true population value mu. Now, imagine a thought experiment for a while. We've now worked out that the sampling distribution of X bar has a shape which is normal by the central limit theorem, a mean equal to mu, in other words it's an unbiased estimate, on average it gets it right, and a variance equal to sigma squared on n. The more data you've got in your sample, the more accurately you're going to estimate the true value mu. So if you were, again, in an artificial world, to know the truth, to know that the true value of the mean is 10 and the standard deviation is 2, or the variance is 4, then you could work out what's the probability if the true value of the mean is 10, what's the probability of getting an X bar bigger than 11, for example. Why you want to calculate a probability like that is not totally clear yet. That'll become apparent in a couple more videos, but just trust me that that's quantity that you could work out if you wanted to. So here we are, we work it out, probability of X bar being bigger than 11, we just standardise, subtract the mean, divide by the standard deviation, get a standardised value for Z, go to the norm dist values in Excel, and out spits a probability. And so on the other hand, if instead of a sample of 25 I had a sample of 64, I could do the same calculation. The only difference is that instead of 4 on 25, I've now got 4 on 64. So my Z value is slightly different and my probability is a bit different. My probability now is even smaller than it was before. So if you've got a sample of 25, chances of getting a value of X bar bigger than 11 is quite small. If you've got a sample of 64, the chances of getting an X bar bigger than 11 is even smaller when the truth is 10. Okay? So that's just sort of calculations we can do. As I say, at the moment, it's not totally clear how that's useful to us, but it kind of, the thought process is sort of the following. Suppose we thought 10 was some important number to us. You know, 10 is the number of doctor's visits that people, elderly people tend to take in a year, say. And then that's historically what it's been. So typically we've seen an average of 10 doctor's visits per year for elderly people. And then we take a sample of elderly people and we get an X bar of 11, and we think, or 11.5 or something. We think that seems like it's an increase on the past. But maybe that was just a fluke, because remember, X bar is only an estimate of the truth. But what this statement says is that if I'd taken a sample of 25, that if the true number of doctor's visits is still only 10, it'd be pretty unlikely that you would get an X bar bigger than 11. Less than a 1% chance of that occurring. So that suggests maybe this sample mean is not a fluke, and maybe indeed there has been an increase in the number of doctor's visits people are taking. That's kind of the way we use quantities like that. That's the intuition. We'll do that a little bit more formally when we talk about hypothesis testing in a while. For now, the other way we can use this thing called the sampling distribution to give us insight into uncertainty is with what we call a confidence interval. Now, we use confidence intervals all the time when in everyday usage, when people say, what's the temperature going to be tomorrow? And you say, the forecast is for 25, for example. But, it could be a little hotter, it could be a little cooler. And then someone says, how accurate are they normally? They normally get it right to within sort of 1 or 2 degrees, so it may not be 25, but it's almost certainly going to be somewhere between 23 and 27. Now, that's a confidence interval you've just given. So what we can do is make use of a little bit of mathematics to manipulate our sampling distribution of X bar to get a method for calculating a confidence interval for a particular set of data. And then we can say the kind of statement I just made with a bit of statistical theory to justify it rather than just sort of common intuition. So a confidence interval is a range of values within which we are pretty sure that mu lies, and we construct that confidence interval just based on the sample of data we've got. So the last line kind of gives us the conclusion, and the starting point gives us the beginning point for getting there. So let's just look at the last line. This says that I'm 95% sure that the true value of mu is going to lie somewhere between X bar minus 1.96 times the standard deviation on n and X bar plus 1.96 times the standard deviation on n. So this might be that I'm pretty sure that the temperature is going to be somewhere between 23 and 27 degrees, for example, would be an application of that kind of result. So that's the mathematical way we represent a confidence interval. We get there by the starting point being the sampling distribution of the X bar, which is given to us here. X bar's got a mean of mu and a standard deviation of variance of sigma squared on n. So we standardize it by subtracting the mean and dividing by the standard deviation. And then we say the 1.96 and plus 1.96 and minus 1.96 are the Z values that you need in order to give you a 95% probability of being between these two values. So you get that from the normal tables. You then transform the X bar distribution into a distribution around a probability statement around mu by just rearranging all of these different steps here, and you end up with this statement down here. You'll see this how this works mechanically in a little while. So, but the key important point here is, with just the information from my sample, I don't actually know mu, but I'll get to that in a moment. With just the information from my sample, I can now calculate these two things here, the lower bound and the upper bound, and they give me a statement about where I believe the mu is likely to lie. So I've got a sample of 11 doctor's visits for these elderly people per year, and say, for simplicity, suppose sigma to the square root of n was 0.5. So roughly speaking, it's 2 times 0.5, so I get a value of 1 for this quantity here, 1.96 times this. So I'm pretty sure that the true value of the mean number of doctor's visits is somewhere between 11 minus 1 and 11 plus 1. So I've estimated the true value to within plus or minus 1 from my sample value. So I'm pretty sure that it's somewhere between 10 and 12 doctor's visits per year, for example, of elderly people. Now, then you come along and you say, well, I've got a bit more money. I'm going to sample, lots more people and get a more accurate estimate of the thing. So I get a value of 11.2, for example, for my sample mean. And my n is a lot bigger. So this quantity here now is not 0.5 anymore. It's 0.3, say, if I've got about 4 times the sample size. So 2 times 0.3 is 0.6. So now I've got 11.2 minus 0.6, 11.2 plus 0.6. So now I come along with another sample, bigger n, and I can say that I'm 95% sure now that the population mean is somewhere between 11.2 minus 0.6, so that's 10.6, and 11.2 plus 0.6, that's 10.8. So I'm 95% sure that the true mean is between 10.6 and 11.8. Okay, so that's the kind of way in which we've now been able to send the message to the people who use our statistical analysis that we don't really know the truth, we're simply estimating the truth, but we're giving them some indication of how accurate our measure is. So if it really matters here that they, for example, have enough doctors to cope with all the doctors' visits, they better make allow for the possibility that the true number of visits could be as high as 11.8 or even more. There's a cautious approach that they might take. If this was an essential service, they want to make sure they've got enough people to provide access to the services, then they plan on the basis of their conservative estimate. So that's just one throwaway line example of how the use of this uncertainty really matters if you're providing, depending on how you're actually using it. Okay, but the main message is that we are coming up with a few different ways here of reflecting that uncertainty, and particularly the one that with the most concrete and commonly used one is this idea of a confidence interval. Now there's one little qualifier to make here. I don't know sigma in any given case, so what I have to do is replace sigma with my sample standard deviation, and so the formulas that I use are actually these ones here to calculate my confidence intervals. Sigma has been replaced by S, and Z has been replaced by the t distribution. You recall we used the t distribution in a previous video, and the t distribution is quite like the Z distribution, very similar shape, bell-shaped curve, just a little bit wider to reflect the fact that we've got another element of uncertainty here. We've estimated we've got one more source of uncertainty, the fact that we've estimated the mean the standard deviation instead of using the true standard deviation. So we get a slightly wider confidence interval due to that extra level of uncertainty. So the bottom line in practical terms is you just need to know how to calculate these confidence intervals and interpret them. Where they come from is the idea of a sampling distribution and some of the manipulation of that sampling distribution that we've derived in this video. Okay, a little bit more practical about confidence intervals coming up soon. Thanks.